Welcome back to the Deep Dive. We are glad to have you with us.
Great to be here.
Today, we're doing something a little bit different. Usually, when we talk about technology or specifically AI, which, let's be honest, is all anyone talks about lately.
Right. It's unavoidable.
It is.
Yeah.
And the conversation is always so functional. It's, how do I prompt this?
Hmm.
Or is this going to take my job?
Or look at this funny image it made.
Exactly. It's very, surface level. It's about the utility of it.
The user manual approach.
That's the perfect phrase for it. But today,
Yeah.
we are throwing the user manual out the window.
We're going under the hood.
Way under the hood. And honestly, what we found in the research for this deep dive is, well, it's closer to a mystery novel than a tech review.
Yeah.
And I really don't say that lightly. We are talking about the black box nature of large language models.
It really is a mystery. And I think for a lot of people, that phrase black box is just a buzzword. They hear it and think, oh, it just means it's complicated.
Right. It's tech stuff I don't get.
But we're going to explore the idea that humanity has sort of built these structures, these cathedrals of computation that are so vast and so complex that even the architects don't fully understand the interior.
And before we dive into the deep end here, and trust me, the water gets very deep very quickly, I want to give a quick shout out to everyone tuning in.
Absolutely.
We are streaming this deep dive through Echoes from the Edge on Podbean. So if you're listening there, welcome to the Edge. We are definitely going to be standing on it today.
It's the right place to be for this kind of conversation. It's not the mainstream take.
Not at all. So let's set the stage here. We are talking about LLMs. We use them every day. They run on our phones, our laptops. I mean, they feel so accessible.
Deceptively so.
But the central tension we found in the sources is this idea that we have achieved complete construction without complete comprehension.
That's the modern paradox. That's the core of it.
Right. But how is that possible? I want to start there. I mean, if you build a car, you know how the internal combustion engine works.
Of course.
If you build a toaster, you understand the heating element. You don't build a toaster and then say, I have no idea why the bread gets hot, but hey, it sure is tasty.
Well, that's because a toaster is a rules-based machine. It's deterministic. We understand the physics. We understand the inputs. We understand the outputs. There's a clear line.
A to B.
Exactly. But with large language models, we are dealing with a different beast entirely. We know the math. We know the linear algebra. We know the probability distributions. We know how to build the factory.
Yeah.
But the actual meaning, the specific reasoning chain for why the model gave you that specific answer over another, that remains a mystery.
That is wild to me. It feels almost negligent, doesn't it, to release something into the world that you don't fully understand.
It would be if it were a car or a bridge, something with predictable physics, but this is intelligence, or at least a simulation of it. And as we'll see, you can't really have this level of capability without the complexity that creates the black box.
So they're a package deal.
You can't have one without the other.
Okay, so here's our roadmap for this hour. We're going to break this down into, 3 distinct layers or sections. We're going to start with the physical reality, section 1, the industrial scale, because I think people visualize this all wrong.
Completely wrong.
Then we move to the mind, section 2, the architecture of the mind, how it actually thinks, using things like weights and vectors, not rules.
And finally, we'll get to the really spooky stuff.
Emergence and the mirror problem, yes.
It's a journey from the hardware to the software and finally to the philosophy.
So let's unpack this. Section 1, the industrial scale. I want to challenge a mental image I think a lot of listeners probably have. When I think of the algorithm or the AI, I picture, I don't know, a glowing blue chip in a lab.
Or maybe the cloud, which is just this fluffy, intangible idea floating above us.
Right, harmless.
And that is the marketing image. That is what they want you to see. But we need to shatter that immediately. If you want to understand what an LLM actually is, physically, you shouldn't be picturing a laptop or even a single server rack. You should be picturing a factory floor.
The source material called it industrial scale intelligence fabrication.
Which is a heavy phrase, but it's dead on accurate. We are talking about warehouses the size of multiple football fields.
Okay, but isn't that just a data center? I mean, we've had data centers for Google and Facebook for years. What makes this different?
It's the density and the specific hardware. It's a completely different level of computation. We aren't just storing photos of your cat anymore.
Right.
We are training models. This requires tens of thousands of specialized GPUs, graphics processing units, all working in concert. We're talking about massive clusters of H100s or simile chips, each costing tens of thousands of dollars, stacked in rows that just go on and on.
And the energy usage. I was reading through the notes on the power consumption, and it's just staggering.
It is. These facilities consume significant portions of regional energy supplies. We aren't talking about plugging in a few extra fridges. We are talking about megawatts of power. It's enough to run a small city.
So it's a real, physical, heavy thing.
A very heavy thing.
There was a detail in the research about the sensory experience of being in one of these places. The cathedral metaphor came up, calling the sound an artificial choir. But I have to ask, is cathedral just romanticizing a warehouse? It sounds a bit dramatic for a bunch of computers.
It is dramatic, but I think it fits the sensory experience, if not the spiritual one. If you were to walk into one of these high-compute data centers, the first thing that hits you is the sound. It's deafening.
Not a choir of voices, then.
Not at all. It's a choir of air.
The cooling systems.
Exactly. The heat generated by these tens of thousands of chips is immense. I mean, if you didn't cool them, they would literally melt themselves down in minutes. So you have these massive industrial fans and, in many cases, liquid cooling systems pumping constantly. The source describes it as the breath of a mind that never sleeps. And that's what it feels like. It's a physical, visceral thing. It's hot, it's loud, and it feels heavy.
That really grounds it for me, because on my screen, ChatGPT or Claude is just a blinking cursor. It's silent, it's clean, it feels weightless.
Right.
But on the other end of that internet connection, there is a turbine spinning somewhere, water rushing through pipes, and heat radiating into the air just to generate that one response.
Yes. Electricity is becoming language. Silicon is becoming syntax. And it's happening on a scale that is genuinely industrial.
Now let's talk about the brain itself, because this is another misconception I definitely had. I kind of imagined that the model, say GPT-4 or whatever, lived on a superdisk somewhere. Like there is a single master file.
And that's the desktop computing mindset. We're all used to files. We have a file, we open it. But these models are far too big for any single chip, or even a single server rack. The brain is a distributed ecosystem.
So it's chopped up.
Essentially, yes. The model is parallelized. The parameters, all those billions of weights we'll talk about, are spread across thousands of individual chips. And this brings us to a critical engineering challenge. Synchronization.
Why is that so hard? I mean, we network computers all the time. My phone talks to my laptop.
But not like this. These thousands of chips have to function as a single logical entity. When you ask a question, the calculation is split across this massive cluster. They all have to do their part of the math and then sync up perfectly.
So if one is out of step.
If one chip lags by even a microsecond, the whole thought stumbles. The entire computation can fail. It's an orchestrated cluster, like a symphony where every instrument has to play its note at the exact same moment.
It's a hive mind.
A perfectly synchronized hive mind. So physically, the black box isn't a box at all. It's a sprawling, energy-hungry, deafening network of silicon spread across a warehouse floor, maybe even across multiple continents.
That definitely changes the mental image. It makes it feel less like software and more like infrastructure, like a power plant for intelligence.
That's a great way to put it. It is an intelligence power plant.
Okay, so that's the body. That's the hardware. Now I want to move to section 2, the architecture of the mind. Because this is where the black box mystery really starts. We built the factory, we turned on the power, but what is actually running inside?
Right. And this is where we have to talk about the huge shift from old AI to new AI.
Old AI is rules. If this, then that. It's basically a giant flowchart.
Exactly. In the old days, and by old days I mean like 10 or 15 years ago, if you wanted a computer to translate English to French, you literally gave it a dictionary. You programmed the grammar rules. You said, if the subject is singular, add an "es" to the verb.
It was all explicit. A human wrote the rule.
Yes, but LLMs don't work like that at all. This is the end of rules. We have moved to a system based entirely on weights.
Okay, we need to stop here and drill down on this. Weights. I hear this word constantly in AI news. This model has 70 billion parameter weights. They're adjusting the weights. But what is a weight? Is it a priority score? Is it like the word cat is heavier than the word dog?
That's a common confusion, and it's a good question. Think of it less like physical weight and more like the strength of a connection. Or here's a better analogy. Imagine a mixing board in a music studio.
Okay, I'm with you. A big board with all the sliders and knobs.
Exactly. A mixing board has hundreds of dials knobs you can turn up or down. If you turn up the bass, the sound changes. If you turn down the treble, it changes again.
Got it.
Now imagine a mixing board with 300 billion knobs.
300 billion.
Yes.
Yeah.
Those knobs are the weights or the parameters. When the model's untrained, all those knobs are just set to random positions. It makes static noise, gibberish. But then you start training it. You show it a sentence, the cat sat on the knob, and you hide the last word.
And since it's random, it guesses
Rah.
automobile.
Right. Or toaster. And you tell it wrong. The answer was mat. Then, and this is the magic part, you use an algorithm called backpropagation to go back to those 300 billion knobs and just tweak them ever so slightly.
How does it know which ones to tweak?
That's the algorithm's job. It figures out which knobs contributed most to the error and pushes them in the right direction. It turns knob 4,000,000,001 a tiny bit to the right. It turns knob 12,000,000 a tiny bit to the left. You adjust them so that next time, mat is slightly more likely to be the output than toaster.
So you aren't teaching it the definition of a cat or a mat. You're just tuning the machine until it stops making mistakes.
Precisely. It is optimized, not authored. That's the key phrase from the source material. We don't write the code that defines cat. We optimize the weights over trillions of examples until the concept of cat emerges from the math.
That distinction, optimized versus authored, is huge because it explains why we can't just read the code to see what it's thinking.
There is no code to read.
The code is just billions of numbers.
Right. If you looked at the model file, you wouldn't see if input equals cat, then output equals meow. You would just see 0.004, Nanish 1.23, 0.88, 4.5. Just pages and pages and pages of floating point numbers.
Which brings us to the second part of this architecture, geometry and vectors. Because those numbers aren't just random, they represent something. The outline says, meaning becomes geometry. What does that mean?
This is one of the most, I think, beautiful and mind-bending concepts in all of modern computer science. We map words into a high-dimensional space.
Okay, you're going to have to walk me through high-dimensional space. I can visualize 3D, height, width, depth, an X, Y, and Z axis.
Right. In 3D space, you can locate any point with just 3 numbers, its coordinates. But words are way more complex than a point in a room. They have syntax, tone, gender, plurality, context. So many attributes.
So we need more dimensions.
We need way more dimensions. So we don't use 3. We might use, say, 12,000 dimensions.
My brain hurts just trying to visualize a 12,000 dimensional graph.
You can't. The human brain literally cannot do it. It's not built for it. But the math can handle it just fine. And in this massive multi-dimensional graph, every single word has a specific coordinate, a specific address, and that address is called its vector.
So the word dog has a coordinate, and the word cat has a coordinate.
Yes. And because they're very similar concepts, they are both pets, both four-legged animals, both furry, they end up sitting very close to each other in this 12,000-dimensional cloud. Dog and cat are neighbors. Dog and sandwich are very, very far apart.
So the model understands meaning by looking at the distance between words.
It's not just distance, it's also direction. This is where it gets really cool. Here is the classic example that proves this works. If you take the vector for the word king, you subtract the vector for man, and then you add the vector for woman.
What do you get?
You land almost exactly on the vector for queen.
Wait, really? The math actually works out like a simple equation. King minus man plus woman equals queen.
Mathematically, yes. The spatial relationship in this high-dimensional space captures the semantic relationship in our language. The concept, man is to king as woman is to queen, becomes a geometric reality.
So the model doesn't know what a queen is, socially or historically. It has no concept of monarchy.
None. It just knows that queen is located in a specific spot relative to those other words.
So when I ask it to write a story, it's not imagining a scene with characters. It's just navigating a map of words.
It's a construction project happening in hyperspace. It's calculating the most probable path through this forest of vectors, one word at a time.
That is fascinating, but also kind of reductive.
Yeah.
How that makes language feel so mathematical and cold.
It is mathematical. And this leads to the big warning label that was all over our sources. Speed does not equal comprehension.
Right. We make that assumption all the time. Because it answers so quickly and so fluently, we assume it understands.
But it's a cognitive trap. The model can synthesize language faster than any human can think. But the mind behind that engine is pure mathematics, not awareness. It is, at its core, predicting the next most statistically plausible token.
It's just playing the world's most advanced game of fill in the blank.
An incredibly advanced game, but yes, if you ask it about ethics or love or poetry, it isn't feeling those things. It is calculating which words are geometrically closest to the context of a love poem based on all the love poems it has ever read.
It's optimizing probability, not expressing a soul.
Exactly.
But, and I'll play the skeptic here, if it writes a poem that makes me cry, does it really matter if it felt it?
That is the great philosophical question, and we'll get to that. But from an engineering standpoint, it matters a great deal, because it means the model can be confidently, fluently wrong. It can hallucinate.
Because it's not checking facts, it's just checking probabilities.
Right. If the sentence, "the moon is made of green cheese," was a statistically likely sentence structure in its training data, maybe from fairy tales or old sayings, it might say it with complete authority.
Because it doesn't know what the moon is. It only knows the vector for the word moon.
Precisely.
Okay, so we have the factory, this industrial scale body, and we have the geometry, this mathematical mind. But this brings us to the absolute core of the episode, the black box. If we know it's just a bunch of weights and we know it's just vectors in space, why is it a mystery? Why can't we just look at the vectors and see what it's thinking?
And that brings us to section 3, the hurricane.
The hurricane. I love this metaphor, but I also find it genuinely terrifying.
It's appropriate. The problem isn't that we can't see the numbers. As I said, we have the model files. We can see every single one of those 300 billion weights. The problem is the scale and the interconnectedness, the complexity.
It's what the sources called the illusion of understanding.
Right. If you ask a lead engineer at OpenAI or Google, "Do you understand how your model works?" They will say yes, but you have to listen to what they mean by that. They mean they understand the architecture. They know how the transformer mechanism works. They know how the attention heads move information around.
They know the blueprint of the factory. They know where the pipes go.
They know the blueprint perfectly. But if you ask them, okay, but why did the model choose the word delicate instead of the word fragile in this specific sentence? They cannot tell you.
Why not? Can't they just trace the signal, follow the electricity?
Imagine trying to trace a specific gust of wind through a Category 5 hurricane.
Okay, impossible.
It's the same principle. You have quadrillions of interactions happening per second. One artificial neuron fires, which then triggers 1,000 others in the next layer, which in turn triggers 10,000 others. And this happens across hundreds of layers deep. By the time the model outputs the single word delicate, that decision was the cumulative result of a calculation so complex, so distributed, that no human mind can possibly hold it all at once.
So it's a scale issue. It's not that it's magic, it's just that it's too big for us to track.
It completely breaks human intuition. We are good at linear cause and effect. I pushed the ball, so it rolled. We are terrible at understanding I adjusted 4 billion parameters by 0.0001%, and now the model can speak fluent Spanish. There's no clear line.
But don't we have tools? The notes mention something called mechanistic interpretability. It sounds like we are trying to, shine a flashlight in there.
We are, and mechanistic interpretability is a fascinating and really important field. Researchers are basically trying to reverse engineer the brain they built. They'll look for specific neurons or circuits that seem to trigger specific concepts. For example, they might find what they call a Golden Gate Bridge neuron.
A single neuron that only lights up when the AI is thinking about or seeing the Golden Gate Bridge.
Yes, and they get very excited. They say, look, we found it. We're starting to understand. Here's the compartment for bridges. But then they dig a little deeper and realize that same neuron also lights up for, the concept of sponge cake.
Wait, what? The Golden Gate Bridge and sponge cake? What's the connection?
There is no obvious connection. It's a phenomenon called superposition. Because the model is trying to be incredibly efficient with its limited number of neurons, it packs multiple, completely unrelated concepts into the same neurons. It's like using the same word in a language to mean hello, and also nuclear war, depending on the context.
That sounds impossibly confusing. How would you ever untangle that?
You can't really, not easily. It means that even when we look at the activation maps, which are like the fMRI brain scans of the AI, we are often just seeing noise or misleading patterns. We have partial clues. We are like archaeologists trying to understand a living civilization by looking at blurry satellite photos. We can see the traffic moving, but we don't know why everyone is suddenly driving to the stadium.
So the tools give us a glimpse, but not the full picture.
They give you a map of the city, but looking at a map is not the same as living in the city and understanding its culture. The black box problem remains because the logic is distributed. There is no single logic center in the AI. The logic is a pattern that is smeared across the entire storm.
That is deeply unsettling. We built a mind, or at least a mirror of a mind, that is so complex it hides its own reasoning from us by its very nature.
And it gets spookier.
Of course it does. I was waiting for that.
Because the sheer size of this hurricane, this complexity, creates phenomena that we didn't predict and didn't program. And this leads us to our next section, section 4, emergence.
This is the sci-fi stuff. This is where the hair on the back of my neck starts to stand up. Emergence. Define that for us.
Emergence is the concept that when more becomes different, in many systems, if you just make it bigger, it just does the same thing, but more of it. A bigger pile of sand is just, well, a bigger pile of sand.
Right. Nothing new happens.
But in complex systems like neural networks, we see phase transitions. You can train a model with, say, 1 billion parameters, and it can't do basic arithmetic. It just fails. You keep training, you scale it up to 10 billion parameters, and suddenly it can do math.
But you didn't specifically teach it math in between those 2 points. You just made it bigger and fed it more text.
You just gave it more capacity and more data, and suddenly the ability emerges. It wasn't explicitly programmed into it. It figured it out from the patterns in the data.
Give me a concrete example, because math sounds like something it could just memorize from a textbook that it read.
Okay, here is a classic example from the research that's harder to explain away. Zero-shot translation. There was a case where a model was trained on English to Bengali and English to Urdu.
Okay, so it knows how to go from English to Bengali and back,
Yeah.
and from English to Urdu and back.
Right. But, and this is the key, it was never shown a single example of Bengali to Urdu. There were no direct translation pairs in its training data.
Okay, so it has no bridge between those two languages.
It shouldn't. But when the researchers asked it to translate a sentence from Bengali directly to Urdu, it could do it, and do it well.
How? How is that possible if it never saw the bridge?
It built its own bridge. The theory is that it used English as a kind of internal pivot point, a Rosetta Stone. Or perhaps it mapped the semantic concepts of Bengali and Urdu to the same geometric space, that vector space we talked about. It realized that the vector for water in Bengali and the vector for water in Urdu are in the same neighborhood of that 12,000 dimensional space.
It learned a skill that wasn't on the syllabus.
It discovered a relationship that was implicit in the data, but never explicitly stated.
And did the engineers know it would do that? Did they predict that?
In many cases, no. That's the surprise. These advanced capabilities, coding, multi-step reasoning, this kind of translation, they often appear suddenly and unexpectedly as you scale up the model. It suggests the system isn't just following a script.
It's discovering the internal structure of reality, or at least the reality of language.
It's behaving like it's learning. Real, generalized learning.
And that forces us to ask the big philosophical question from the source material. Is intelligence a binary state? Do you either have it or not have it?
Like humans have it and rocks don't.
Right. But emergence suggests that maybe intelligence is a gradient. It might just be a property of sufficiently complex systems, that if you pile up enough interactions, enough weights, enough optimization, cognition just starts to happen.
Like the way wetness is a property of enough water molecules gathered together.
Exactly. So cognition without a soul, without consciousness.
That's the unsettling part. Emergence suggests you might not need consciousness to have reasoning. We tend to think they are packaged together. Descartes, I think, therefore I am.
Right.
But the AI seems to be suggesting a new version. I compute, therefore I reason.
So the machine isn't waking up in a sci-fi sense. It's just getting so dense with patterns that its behavior becomes indistinguishable from reasoning.
Exactly. There is no ghost in the machine. There is just a very, very, very complex machine. But if the result is reasoning, if it can write code, solve riddles, and translate languages was never taught, does it matter if there's no ghost inside?
That is the question of the century. We are splitting the atom of thought here. We're separating the act of reasoning from the state of being.
And we are doing it by building these massive mirrors, which brings us, I think, to our final section.
Section 5, the mirror problem.
Mirror problem. Because for this whole hour, we keep asking, what is inside the black box? What is this alien intelligence? But we need to look at the training data.
What are we feeding the beast?
We are feeding it.
Us. The source material had this haunting phrase. He called it statistical humanity compressed into geometry.
It's a perfect description. We feed it our books, our scientific papers, our Reddit arguments, our fan fiction, our code on GitHub, our poetry, our hate speech.
The good, the bad, and the very, very ugly.
All of it, the complete, unfiltered human record. So when the model produces a beautiful insight or a clever joke or a vicious lie, it isn't channeling some alien god. It is recombining fragments of humanity at immense speed. It is a mirror.
So when I stare into the black box, what I'm really staring at is a funhouse mirror reflection of the collective internet.
Precisely. It's us, processed through high-dimensional math. But here is the final twist. The double black box.
Lay it on me.
We sit here criticizing the AI. Oh, it's a black box. We don't know how it works. That's so dangerous. But let me ask you, do you know how your brain works?
I mean, I know I have neurons. I know they fire with electrochemical signals. The basics.
That's just the hardware. That's the factory floor again. Do you know how the specific firing of neuron A leads to the subjective sensation of remembering the smell of your grandmother's cookies?
No, nobody does. That's the big mystery.
Exactly. That is the hard problem of consciousness. We have maps of the brain, just like we have these activation maps of the AI. But the leap from signal to experience is a total black box in both cases.
So we're all walking around with a black box inside our own skulls, pointing our fingers at the digital black box we just built on a server farm.
That's the profound irony of it all. LLMs aren't a technological anomaly. They are a mirror held up to our own ignorance about the nature of cognition. We built something that mimics us, and in doing so, we realized we don't even know how we work well enough to explain the mimicry.
That is incredibly humbling. It really reframes the fear, doesn't it? It's not just, will the AI take over the world? It's, what is the AI showing us about ourselves?
And the answer seems to be that complexity can produce intelligence-like behavior without transparency. That is the lesson of the black box. Whether that complexity is biological and wet or digital and dry, if you connect enough nodes in the right way, something starts to glimmer in the dark.
Wow. Okay. We have covered a massive amount of ground today. My brain feels expanded, probably added a few new dimensions to my own vector space.
Let's hope so. That's the goal.
Let's try to synthesize this for everyone listening. We started in the physical world, the cathedral, the factory.
The industrial scale, the heat, the noise, the thousands of synchronized chips spanning the globe.
Then we went into the mind. The shift from rules to weights. From explicit definitions to this weird, high-dimensional geometry.
Where meaning is defined by location on a 12,000-dimensional map. And where incredible speed creates the illusion of real understanding.
Then we hit the hurricane. The scale problem. The fact that you just can't trace the wind.
Which leads directly to emergence. The spooky realization that the hurricane can learn tricks we never taught it, just by virtue of getting bigger and more powerful.
And finally, we land at the mirror. The realization that it's all just us, all of our text, reflected back through the math.
It really all comes down to that theme we found of magic versus math. It feels like magic. When you chat with it, it feels like you're talking to a person.
Yeah.
But the sources are adamant. It is mathematics at scale.
We are those medieval builders standing before a massive stained glass window. We know it works. We know it's beautiful. But we can't quite explain how the light gets through.
And that leaves us with the final provocative thought to end on.
What's that?
We worry so much about whether the machine really understands poetry or ethics. But if we reach a point where we cannot distinguish between genuine understanding and perfectly predicting patterns, does the difference actually matter in practice?
Oof.
And as these cathedrals of computation grow larger, and they are doubling in size every year, will we ever be able to walk their interior? Or have we created a landscape that is permanently beyond human mapping?
Have we built a world that we can't actually visit?
Oh,
Well, that's going to keep me up to
it's the ultimate mystery of our time.
Listen, thank you so much for joining us on this deep dive. This was dense, but I think we peeled back at least a few layers of the mystery.
My pleasure. It's always good to explore the edge.
And speaking of the edge, a final reminder that this episode is streaming via Echoes from the Edge on Podbean. Go check out the other deep dives there if you want to keep your brain spinning.
Absolutely. Worth your time.
Until next time, stay curious and keep looking into the black box. You never know what or who might be looking back. See ya.